Hello. In the previous lecture, we discussed many properties of the ring after adding an algebraic element to a field F. So among other things, we showed that F bracket alpha is a field, and this was proved based on the fact that F bracket alpha is isomorphic to the quotient ring of the ring of polynomials by the principal ideal generated by the minimal polynomial of this algebraic element. And we showed that this minimal polynomial is an irreducible polynomial. And then based on the fact that the ideal generated by an irreducible element in a PID is always maximal, we deduced that the F bracket alpha is a field. Using the same quotient and using long division, we deduced that every element of F bracket alpha can be uniquely written as an F linear combination of 1 alpha to the dot till alpha to power n minus 1. And what is n? N is precisely the degree of the minimal polynomial. So we see again and again the importance of understanding the minimal polynomial of alpha over F. So what is the minimal polynomial again? This is the smallest polynomial with coefficients inside F that has alpha as a 0. What do we mean by the smallest? So definitely we can say the smallest degree among non-zero polynomials that have alpha as a 0. But we can do better, and we say that if F has alpha as a 0 and this F has coefficients in the field capital F, then it should be a multiple of the minimal polynomial. So essentially all the polynomials that have alpha as a 0 form an ideal, and that ideal is the principal ideal generated by the minimal polynomial of alpha over F. So again, we see the importance of understanding that the minimal polynomial. And last thing that we showed is a kind of characterization of minimal polynomials. And it says that a polynomial P is the minimal polynomial of alpha over F, precisely when, first of all, alpha should be a 0 of this. Second, P should be monic. This condition is not that crucial because we can always multiply by the inverse of the leading term and end up getting a polynomial that is monic. But the crucial condition is that P should be also irreducible in the ring of polynomials with coefficients inside F. We also described that irreducibility in the field of polynomials with coefficients inside a field is precisely what we had learned earlier in middle school. What is it? That a polynomial is irreducible when it's not constant and it cannot be written as a product of smaller degree polynomials with coefficients inside the same field. So this is the last condition that can help us to understand the minimal polynomial, to find the minimal polynomial. And in order to use the last condition, we need to come up with a mechanism to find out whether or not a given polynomial is irreducible. So we will come up with a series of criteria that can help us to decide whether or not a polynomial is irreducible. So let's say my polynomial is smallest degree possible, meaning degree 1. In that case, whenever I give you a field, and then a polynomial of degree 1 is always irreducible. That is rather easy because smaller degree polynomials means they should be constant, but I can never multiply two constant polynomials and end up getting a polynomial of degree 1. This means that if I give you a polynomial of degree 1 with coefficients inside a field, it is automatically irreducible. And one thing else that we observe is that it also has a 0, essentially because the polynomial is of the form a constant plus a sub 1 times x, where the coefficient of x is not 0. Again, because we are working in a field, every non-zero element is a unit. So essentially, we can multiply by the inverse of the leading coefficient and find a 0 for such a polynomial. So a degree 1 polynomial always has a 0 within the same field, and it is always irreducible in F bracket X. How about degree 2 polynomials? So a degree 2 polynomial, or let's say even more, so a polynomial that has degree at least 2, as soon as it has a 0, it cannot be irreducible anymore. So having a 0 automatically rules out being irreducible if my polynomial has degree at least 2. Why is that the case? It's essentially the factor theorem. Because if f has a 0, then I can factor out x minus the 0 that we have. And from there, because we are assuming that degree of f is at least 2, we get 2 factors. Both of them have degree smaller than degree of f. So that's why if a polynomial has degree at least, 2, then having a 0 implies that it cannot be an irreducible polynomial inside this ring. Now, the nice thing is that if my degree is either 2 or 3, then being irreducible or not is equivalent to saying that f doesn't have a 0 or it has. And it is rather easier to find out whether or not a function, a polynomial, has a 0 than to find out if it can be splitted into different factors. Okay, so let's again say the statement. Assuming that the degree of f is either 2 or 3, then f is irreducible if and only if it does not have a 0 inside the field. Okay, let's see how the proof goes. We're going to go through the proofs that I just mentioned as well. So again, if the degree of f is 1, automatically it's not constant. And if I write it as a product of 2 polynomials, then one of them should be of degree 1. So that means it cannot be written as a product of a smaller degree polynomials. Okay, and if I tell you that f has degree 1, then it is of this form, and the leading coefficient is not 0. I mean, that's the definition. A1 is the leading coefficient, and therefore I can solve for x. I can set it equal to 0 and solve for x, and I get that negative A1 inverse A sub 0, which is an element of the field, is a 0 of this degree 1 pi. Now, when I look at any polynomial, if I tell you A is a 0 of this polynomial, then by the factor theorem, we can deduce that I can factor out x minus a. That means I can write down f as a product of x minus a times a polynomial with coefficients inside f. So that means the degree of g is 1 less than degree of f, so it is definitely less than degree of f. And degree of g x minus 1, the other factor, is 1, which is strictly less than degree of f, because we assume that degree of f is at least 2. So overall, we deduce that such a polynomial cannot be irreducible in the ring of polynomials with coefficients inside f. Okay, so having the 0, knowing that degree is at least 2 excludes irreducibility. But what if, how about the other way around? Meaning, if I do know that my polynomial is not irreducible, can I deduce that it has a 0? So in general, the answer is no. So if I know f is not irreducible, it does not in general mean that it has a 0. So for instance, x squared plus 1 times x squared plus 2 does not have a 0 in real numbers, but this product is not irreducible either. I'm writing it as product of two polynomials. So in general, we cannot, knowing that a polynomial does not have a zero does not imply that it is irreducible. But this is the case when the polynomial has degree either 2 or 3. You see this one has degree 4. Okay, let's see why. So suppose that I'm giving you a polynomial f, and suppose that it has either degree 2 or degree 3, and assume that it is not irreducible. So suppose that it's not irreducible, then what does that mean? This means I can write f as a product of two polynomials, let's call them g and h, so that degree of both of them is strictly less than degree of f. This condition is always the same as saying that neither of them are constant polynomials. So whenever I tell you that f is not irreducible, this means I can write it as a product of two smaller degree polynomials. In particular, this means neither of these smaller degree polynomials can be constant polynomials. So this is what I'm writing over here. And now you also notice that their degree of these non-constant polynomials, they add up to a number that's either 2 or 3. So that means one of them should be 1. I cannot have, so both of them are positive integers, and I cannot have both of them to be at least 2, because in that case, they add up to at least 4. So knowing that they add up to something that is at most 3, and they are positive integers, I deduce that either degree of g is 1 or degree of h is 1. Okay, that means in part 1, we showed that every degree 1 polynomial with coefficients inside the field has a 0 inside the same field. So that means either g has a 0 or h has a 0 inside f. But both of them divide f, small f. So a 0 of g is also a 0 of f. So in either case, either g has a 0 or h has a 0, from both of them we can deduce that f has a 0 inside the same field. And that's exactly what we wanted to show. So assuming that small f is not irreducible and it has degree 2 or 3, we deduce that it has a 0 inside the field. So this is actually pretty strong, and it is called the degree 2, degree 3 criterion, irreducibility criterion. So degree 2, degree 3 irreducibility criterion. Okay, let's see an application of this. Suppose I give you a polynomial with coefficients inside the real numbers, and I tell you that its degree is at least 3 and it is odd. So I'm giving you an odd degree polynomial, and the degree is at least 3. In that case, we want to show that this polynomial is not irreducible in R with coefficients inside the real numbers. Okay, let's see. We want to use the fact that if f has a 0, then it cannot be irreducible. We want to show that such a polynomial always has a 0. Now, what we notice is that because the leading coefficient is 1, is positive, as I let x go to positive infinity, I will end up getting, I will go to positive infinity as well. So this function, this polynomial, gets larger and larger as we let x go to positive infinity. Now, when I let x go to negative infinity, because n is odd, here I'm using the fact that n is odd, we deduce that when x goes to negative infinity, my function gets smaller than whatever number you give it, and that means that this goes to negative infinity. So I have a polynomial, which is a continuous function. At one end, it is negative infinity. It gets smaller than, so definitely at some point, it gets smaller than 0. Let's say here, and at some point it goes to positive infinity. So definitely at some point it is positive. Now by the intermediate value theorem, at some point it should meet the x-axis. So that means that at some point I get 0 value for f. So by the intermediate value theorem, f does have a real 0. A real root, and therefore it cannot be reducible in the ring of polynomials with coefficients inside real numbers. In fact, one can show that every reducible element of R is either degree 1 or degree 2. But this is based on the fact that every polynomial can be decomposed into linear factors over complex numbers. So we'll come back to this later. Okay, so let's see another example. Let's look at the degree 3 polynomial, x to the power 3 minus x plus 1, but as a polynomial with coefficients inside z sub 3 bracket x. So ring of integers modulo 3. So the first part of this example says that this is an irreducible polynomial inside this ring. The second part says that if I look at the factor ring of the ring of polynomials modeled by the principal ideal generated by this polynomial, it is a field and it has order 27. So that would be a first example for you of a field of order 27. Okay, so let's go through the proof. This polynomial has degree 3, and I want to show that it is irreducible. Then you should automatically think about the degree 2, degree 3 irreducibility criterion. And that criterion says that in order to show that this polynomial is irreducible, it's enough to show that it does not have a 0 inside the field z sub 3. Okay, so that is in fact one of your earlier homework assignments. If you think about it, using Fermat's little theorem, we can show that x to the p minus x plus a non-zero constant can never have a 0 in z sub p. In particular, x to the power 3 minus x plus 1 does not have a 0 in z sub 3. And therefore, by the degree 2, degree 3 irreducibility criterion, we can deduce that it is an irreducible polynomial. Okay, so again, this is a degree 3 polynomial, and z sub 3 is a field. So we can use the irreducibility criterion and then just focus on showing that it does not have a 0 in z sub 3. Then by the Fermat's little theorem, we have that a to the power 3 is a for every element of this ring, this field. From here, we deduce that this polynomial indeed does not have a 0. And this finishes the proof of the first part. So it is irreducible inside this ring. Now, z sub 3 is a field, and therefore the ring of polynomials with coefficients in this field is a PID, a principal ideal domain. In a PID, an element, in a PID which is not a field, which is the case here, an element is irreducible if and only if the ideal generated by that element is a maximal ideal. Knowing that x to the 3 minus x plus 1 is irreducible, we deduce that the ideal generated by x to the power 3 minus x plus 1 is a maximal ideal of this ring. And we showed whenever we look at the quotient ring of any ring by a maximal ideal, we always get a field. So therefore, the factor and the quotient ring is a field. Now, how about the number of elements of this? So we have already showed that using long division, we can show whenever we look at a quotient ring of the ring of polynomials with coefficients inside a field by a polynomial of degree n, every element can be represented by a polynomial of degree 3. So in particular, in this case, we get that every element of this quotient ring can be represented in a unique way as can be written in a unique way as a polynomial of degree at most 2. And then we can ask ourselves how many of such polynomials we have. So we have 3 possibilities for a sub 0, 3 possibilities for a sub 1, 3 possibilities for a sub 2, and then all together we get that the number of possibilities for these concepts is 3 times 3 times 3, which is 27, and this finishes the proof of this example. Okay, so this gives us a mechanism to find irreducibility, and from there we found out a field of order 27. Now we see how important it is to understand whether or not a polynomial has a 0. Over rational numbers, we have a fairly effective criterion that can help us determine if a given rational polynomial has a 0 in rational numbers or not. So the first thing that we notice is that whenever I give you a rational polynomial, you can clear the denominators. You can multiply by the greatest common factor, greatest common divisor of all the denominators, and get an integer polynomial. So this means without loss of generality, I can assume that I'm given a polynomial with integer coefficients, a sub i's, and now I want to understand whether or not this polynomial has a rational 0. So suppose that it does. So suppose B over C is a rational 0 of f, and B over C is in the simple form, which means C is of course non-zero and B and C are co-prime. In that case, numerator should divide the constant term and the denominator should divide the leading coefficient. So that's the rational root criterion. So the rational root criterion says that if B over C is a 0 of an integer polynomial, then the numerator, which is B, should divide the constant term, and the denominator, which is C, should divide the leading coefficient. Okay, so this is an extremely important criterion. We will see many applications of this, but for now, let's go through the proof of the rational root criterion. The proof is actually rather easy. We know that f evaluated at B over C is 0. I'm going to clear the denominators, which means I'm going to multiply by C to power n. As I multiply by C to power n, the first term will end up being the leading coefficient times B to the n. So earlier we had B to the n over C to the n. Now C to the n is cancelled out. The next one would be A sub n minus 1. We had B to power n minus 1 over C to power n minus 1. After multiplying by C to the n, a single C remains. The other ones cancels out. And then like that, we end up getting that C to the n times f evaluated at B over C is this expression. And this is supposed to be 0 because B over C is a 0 of this polynomial. Now, what we'll do, we take the first term and move the other ones to the other side, the other terms to the left-hand side. That means that A sub n times B to the n is negative of summation of the other terms. Now, the other terms have a c in common. So I can factor it out. I can use the distribution law and factor out this c, this common c. This means that a sub n times b to the n is negative c times parentheses, and I factor out the rest. I don't care that much about the rest. I just care about the fact that they have a common c and I can factor them out. Similarly, I can I can work with the last term, and I get that a sub n times c to the n is, again, the rest of the terms have a b in common. I can factor out b. So again, it's not very important what the rest are. So the important part is that we have a c here and we have a b here. What does that mean? This means that c indeed divides a sub n times b to the n, and b divides a sub 0 times c to the n. Now, what do we know? B over c was in the simple form. This means they were coprime. So the GCD of B and C are coprime. This means this B and this C, they have no common prime factors. So if I tell you C divides this product and C and B are coprime, I deduce that C divides A sub n. Similarly, when B divides this product and B doesn't divide C, I can deduce that B divides A sub 0. This is called Euclid's lemma, and you've seen it before. But let me quickly recall what is Euclid's lemma. Euclid's lemma says that if x divides y times z, and if I tell you that x and y are coprime, then I can deduce that x divides z. So this is called Euclid's lemma. This is an important lemma. Using this, one can show that a ring of integers has a unique factorization property. But okay, so let's finish the proof. So again, by these divisibilities and Euclid's lemma, the first one implies that the denominator should divide the leading coefficient, and the second one implies that the numerator should divide the constant term. Okay, so let's see an immediate application of this rational root criterion. So if I tell you f is a monic polynomial, monic integer polynomial, meaning I'm assuming that the leading coefficient is 1, then every rational 0 of f is an integer. Moreover, this integer should divide the constant term of the polynomial f. Notice that the constant term of every polynomial is the same as the value of the polynomial at 0. So again, the point is, so the importance of this corollary is the following, that from rational numbers, all of a sudden we can pass to integers. So if, again, let me repeat, if f is a monic integer polynomial, every rational 0 of f is an integer. Moreover, this integer is a divisor of the constant term. Okay, let's see why this is the case. So suppose b over c is a 0 of this polynomial. Then by the rational root criterion, the denominator should divide the leading coefficient. So that means c should divide the leading coefficient, but leading coefficient is 1 because f is monic. The only integer divisors of 1 are plus minus 1. This means c is either minus 1 or plus 1. In either case, we deduce that the fraction b over c is indeed a whole number and it's an integer. Okay, so it's an integer, and again, I can use the rational root criterion and deduce that the numerator, which is b, should divide the constant term, and therefore b over c should divide the constant term. So altogether, we get this result about monic integer polynomials. Now let's make it a bit even simpler. If I happen to know that my polynomial have the leading coefficient 1, it's monic, it's an integer polynomial, and the constant term is also 1. So I don't know anything about the middle points, middle values, I only know the leading coefficient and the constant term. The only thing that I know about the middle ones is, of course, that they are all integers. In that case, if f has a rational 0, then that rational 0 should be either 1 or -1. And all of a sudden, such a complicated question about understanding whether or not this polynomial has a 0 or not boils down to evaluating 1 plus a sub 1 plus a sub 2 till a sub n minus 1 plus 1, and asking yourself whether or not this is 0, or alternate the sign and ask the same questions. So all of a sudden, the question is about adding or subtracting. So this shows the effectiveness of the rational root criterion in order to find out whether or not an integer polynomial has a rational 0. That said, I have to say that the rational root criterion has its own weaknesses. What do I mean by that? So after all, what do? We start with listing all the divisors of the leading coefficient, all the divisors of the constant term, and form quotients, fractions, where the numerator is one of the divisors of the constant term, and the denominator is one of the divisors of the leading coefficient. Next, we have to evaluate our polynomial at these fractions that we are listing. Evaluating a large degree polynomial is not an easy task. So if I have a polynomial and the degree of this polynomial is say 50, and then even if you want to evaluate it at 2, it's a computationally hard question because we are dealing with large numbers. So if we can manage and work with mod 5 numbers, let's say, then we are in luck. Because mod 5 number, we have only 5 possibilities for numbers, and it's much easier to understand, let's say, what is 2 to the n mod 5, no matter what n is, no matter how large n is. So in general, evaluating a polynomial modulo, so to speak, small integer, is not a complicated task. So if we can actually find out whether or not a polynomial mod n has a 0, from computational point of view, should not be very demanding. So the next thing that we want to show is this result, that if I get lucky and manage to find some n for which my polynomial does not have a 0 in integers mod n, then we can deduce that it does not have a 0 in rational numbers. This is a prototypical type of result. So there are many results of this type in algebra that we want to show certain property for rational numbers holds if I have the same property for integers mod n, let's say for n's that do not have small prime factors. Okay, so in this course, we'll see at least 2 instances of this type. So the first one is understanding whether or not a polynomial has a 0. And the second one is about irreducibility. But as I said, this type of result is actually common in algebra. Okay, but let's see how we should go about it. So technically, this lemma, the next lemma that I'm going to write down, which is a rather easy lemma, but this is a formal way of doing this process. So let me just state it. I'm not going to go into the proof of this lemma because it's just bookkeeping. I leave it to you to fill out the details of the proof. But what is it? So whenever I give you a ring homomorphism from any ring A to another ring B, you can extend this ring homomorphism to the ring of polynomials with coefficients inside A to the ring of polynomials with coefficients inside B. Essentially, this extension sends the variable x to x, doesn't change the variable, and what it does is that it applies C, the initial ring homomorphism, to the coefficients. And because when we are working with polynomials, we are essentially multiplying or adding the coefficients, and C respects addition and multiplication, preserves them, we can deduce that this extension is indeed a ring homomorphism. And so therefore, we get an extension of the initial ring homomorphism. And again, if you think about it, if I evaluate the polynomial f at A, and then apply this homomorphism C, it's the same as applying this C to all the coefficients of f, and then evaluating it at C of A. This last equation is much easier than it looks like. When I write it down in a formal way, it might look a bit complicated. So I go over the last equation to understand what it says, and you immediately see how easy it is. So what does this last equation say? It says, when I evaluate this polynomial at A and apply my ring homomorphism C, what do I get? So I evaluate the polynomial at A, I get this. This means I should substitute A for X. Then I apply this ring homomorphism C, but C is a ring homomorphism, so it preserves addition and multiplication. So this means I have to apply C to the coefficients d sub I, and then I have to apply to A and raise it to power I. But this is evaluate the polynomial with coefficients C of di's at C of A. And that's exactly what we were writing. That if, and you see this, the guy inside is a definition of applying C to the polynomial with coefficients d. So this, I mean, that equation at the end of the day boils down to the fact that C is a ring homomorphism. So when I evaluate it, it's like first applying the extended ring homomorphism and then evaluating it. Let's see how this helps and what is the connection between what I wrote over there and having a zero. So this immediately says that if I apply my ring homomorphism, this extended ring homomorphism to a polynomial, you see, the thing that you have to have in mind is something like this. A might be a complicated ring, B should be an easy ring. So you should have this in mind that maybe I can get a nice model, nice quotient of A, where I can actually find out if a polynomial has a zero or not. Then I give you this polynomial f, it's complicated, it is inside the ring A. I apply this ring homomorphism C and put it inside this nicer, smaller ring. There I find out that I got lucky, and this C of f does not have a zero inside this smaller ring B. If this happens, then we can deduce that f does not have a zero in the initial ring A as well. So it seems that my Zoom screen hanged. So let me see. I have to share it again. Okay, so now it works. That's good. So C of f does not have a zero in B. Okay, that means f does not have a zero in A. So this is a type of example I have in mind. So B is a simple ring. Maybe I get lucky, and inside B, I don't get a zero. From there, we can deduce that we don't have a zero inside A. And the proof is rather easy. Again, if we go and prove the contrapositive statement. So if f does have a zero in A, you simply apply your ring homomorphism, C, to the equation f of a equal to 0. And that means when I evaluate f or C of f at C of a, I'm getting 0. That means this polynomial has a 0 inside the ring B. Okay, so let's see this in action. We call this the Mod and Criterion. What is it? It says that if I tell you a polynomial with integer coefficients is monic, and if I tell you that it does not have a 0 in the ring of integers mod n, then f cannot have a 0 in rational numbers. So all of a sudden, from z sub n, I can pass to rational numbers. So there is a subtlety over here. When I say f does not have a 0 in z sub n, essentially it means I'm replacing f by f mod n. But we often say f does not have a 0 in z sub n, instead of saying that f mod n does not have a 0 in z sub n. Okay, so again, this is part of a family of results in algebra that are of this form, that I want to show certain property holds for z sub n, at least for not large enough, but rather for n's with large enough prime factors. So I should say for large enough prime factors. So the things that I write in parentheses are more technical and they are beyond this course, but nevertheless, that's the truth. So I want to emphasize. So suppose that I want to show certain property is true for, I want to show certain property holds over Q, but the results in algebra tells me that for such a thing to be true, it's enough to show that those properties hold for z sub n when n does not have it does not have a small prime factors. And the way that we usually go about proof of such results is focusing on the contrapositive statement. So we assume that the negation of P holds for Q, and from there we want to deduce that the negation of P holds for Z sub n when n does not have a small prime factors. So the first thing, usually what we do is we consider the contrapositive of the statements. And then what do we do next? Usually what we do, we pass from Q to Z. It's better to say that we pass from Q to some ring that's close to Z, meaning those rational numbers where the denominator is allowed to be only product of some small prime factors. So they cannot have large prime factors. But again, the things in parentheses are beyond this course. So what we do, we try to pass from Q to Z, ring of integers. And then the next thing is to go from ring of integers to Z sub n. Again, if we were allowed to have a small prime factors in the denominator, we have to exclude integers that have a small prime factors in Z sub n. But so again, I'm just giving a schematic kind of steps for these type of results. We typically think about the contrapositive. Then the first step is going from rational numbers to integers. And the next step is going from integers to ring of integers modulo n. Usually the first step is the hard part. It's not that easy to pass from Q to Z. Going from Z to Z sub n, so this step is usually just applying the residual map and using the fact that that's a ring homomorphism with certain care, of course. Okay, so let's go to the proof of the Mod and Criterion. We are given a polynomial. I'm going to look at the contrapositive. This means I'm going to assume that my polynomial does have a 0 in Q. Now, by assumption, f is a monic polynomial, monic integer polynomial. So when we are told that it has a 0, a rational 0, by the rational root criterion we just discussed, we can deduce that it has an integer 0. Okay, so suppose that f of a is 0 for some integer a, and look at this equation mod n. This means a is a 0 of this polynomial in z sub n. So all of a sudden we find a 0 of this polynomial inside the ring of integers modulo n, and that's exactly what we wanted to show. Again, if you think about it, this proof has two parts, going from rational numbers to integers and going from integers to z sub n. And the harder part was the first part, where we used the rational root criterion in order to deduce that we can pass from q to z. Let's see how we can use this mod n criterion. So suppose I give you a prime p, and I give you this polynomial. The polynomial is x raised to power p squared plus p times x to power p squared minus p minus x plus 2p plus 1. That's my polynomial. And my claim is that this polynomial does not have a rational 0. Okay, how can we prove this? We use mod n criterion. So of course, p is singled out here, so that's kind of a hint. We can look at f mod p. You see here we have a choice. We can choose what n we want to choose and what n has a possibility of helping us. Here we are going to choose p and see where we go, where we get to. So if I look at this polynomial mod p, then all of a sudden this term disappears and this term simplifies to 1. So altogether, mod p, I get this polynomial. It is mod f, this is the same as this polynomial mod p, x to power p squared minus x plus 1. I want to show that this polynomial does not have a 0 in z sub p. As soon as I show that this polynomial does not have a 0 in z sub p, using the mod n criterion, I can deduce that it does not have a rational root. Okay, but how can I show that this polynomial does not have a 0? Our key tool is Fermat's little theorem. In fact, that's why it is way easier to compute large powers in mod p numbers. So if I want to compute, okay, so let's see this here, and I'll indicate this later, how we can use Fermat's little theorem in order to expedite calculation of large powers in mod p. So by Fermat's little theorem, for every element of ring of integers mod p, we know that a to the p is a. Now, if I raise both sides to power p, I get that a to power p squared, which is a to power p raised to power p, is again a to the p, and that is a. This means if I raise it to power p to the n, it does not change value of a. So again, from here I can deduce that a to power p to the n is always a. You see, all of a sudden, these large powers of p to the n gets way smaller. I can do this, and whatever number you give me, I can write it in base p, and then, so you give me a large number, I write that guy in base p, I get it is c sub n p to the n plus c sub 0, and using this equality, I can deduce that it is a to power just summation of the digits. So of course, all of these in z sub p. This is why we can evaluate polynomials mod p way faster than what we can do over real numbers, because we can decrease the power quite using Fermat's little theorem in this fashion quite fast. So of course, under the assumption that p is large compared to the power. Okay, so now what? So this means that a to power p squared is a, and therefore we get that this difference is never zero. So I do not have a zero. F does not have a zero in z sub p, and this finishes the proof of this example. Now, we can use this residue map to find out if a polynomial is irreducible or not, and we call that guy Mod P Criterion. And that says that if I give you, let's say, a monic integer polynomial, if I happen to know that f mod a prime number p is irreducible, then we can deduce that it is irreducible in Q. This is actually an extremely important and pretty involved theorem. The proof has the same kind of steps. We look at the contrapositive. We try to pass from rational numbers to integers, and then from integers to z sub p. And similar to the previous time, the hard part, the main difficulty lies in the first step. So going from rational numbers to integers. And our main tool is due to Gauss. It's called Gauss's lemma. So we will prove that in order to do this. But the first thing that we will do in the next lecture is to say the subtlety of having an irreducible element in Q bracket X versus having an irreducible element in Z bracket X. What are the differences? And so that way we will motivate the definition of content of a polynomial. So we'll continue in the next lecture.